As a result of missing section 1.1, I'm going to talk about that section quite quickly. That's the section which, in some sense, reviews vectors and vector notation. Now, you would not have gotten into engineering if you hadn't seen vectors somewhere, I think. For many of you, vectors are arrows that have length and direction and a column of numbers. And that is what vectors are, in some sense. We're just going to try and, I'm not going to talk about them at length. The book does a nice job. I'm just going to review some things that are going to be key for today's lecture. So first of all, at some point, you learned about Cartesian coordinates. And so Cartesian coordinates are, for the plane, you have an infinite plane. You have perpendicular axes. You put equal spaced tick marks along the axes. They might be an inch apart, a mile apart, a light year apart, but they're equally spaced. In high school, you would have called this the x-axis and the y-axis. In linear algebra, we're going to call this the x1 axis and the x2 axis because we're going to be getting out of 3 dimensions quite quickly. If you're in 2 dimensions, you can talk about x and y. If you're in 3 dimensions, you can talk about x, y, and z. But if you're in 25 dimensions or 30 dimensions, you're going to run out of alphabet letters, and also it just gets confusing. So we're going to talk about x1 and x2 instead of x and y. And you remember from some point in your life that every point in the plane can be given a Cartesian coordinate. So this point P would have Cartesian coordinate P1, P2. What that means is that if you go down, this is the distance P1. And if you go across, this is the distance P2. If you're in the first quadrant, P1 and P2 are both, the coordinates are both positive. Here, the first coordinate would be negative, the second coordinate would be positive, but it would still have to do with distances. So these are this is the Cartesian coordinate for this point. Then you have the position vector. So P, which is P1, P2, is the position vector. For the point with the Cartesian coordinates P1, P2. And for example, and then we talk about, so here the language that may or may not be new to you would be position vector. It means the vector that starts at the origin and ends at the point. That might be new. The other language which might be new are coordinates. So as an example, if the vector x is -1, 2, then the first coordinate of x is x1 equals -1. The second coordinate of x is x2 equals 2. And we say that 2 vectors are equal if they are the same size and are equal at each component. So for example, this vector 1, 2, 3, and this vector 1, 2, 3, 4 are not equal because they're different sizes. And these two vectors, 1, 2, 3, 1, 2, 4, are not equal because 3 does not equal 4. These vectors are equal. 1, 1 plus 1, 3. 1, 2, 4 minus 1. Those vectors are equal. Okay, I wanted to start with this example because this is going to be an example where there's a really fast and easy way of showing that the vectors are linearly independent. And that way uses the dot product. And so we're going to now go to the dot product. Now, the dot product, for sure, you have all seen before, because you have all seen vectors before. And so you know from your previous lifetime that the dot product of this is equal to 1 times 2 plus 2 times 6 is equal to 14. And you know from your previous lifetime that 1, 2, 3 dot producted 0 to minus 1 is equal to 1 times 0 plus 2 times 2 plus 3 times minus 1 is equal to 4 minus 3 is 1. So you know this from a previous lifetime. And you also know from a previous lifetime that the dot product between two vectors is equal to the length of u times the length of v times cosine theta. So here you have two vectors. Here's u, here's v. Here is the angle between them, theta. And you know from a previous lifetime that the length of u is the square root of u1 squared plus u2 squared. If u is in R3. And it's equal to the square root of u1 squared plus u2 squared plus u3 squared if u is in, R2, if u is in R3. You may have seen this not with the double bar notation in your previous lifetime. In this current semester, because this book is using double bar, this is the length of u. And we use double bars to disambiguate it from the absolute value. So we can talk about the absolute value of a scalar, and we can talk about the length of the vector, or the norm of the vector. But keep these symbols separate. It'll help keep you sane. It'll remind you of what's what. Now, the proof of this thing, if you're just doing it in R2, this proof is a quick application of the law of cosines, and it's in the book. So if you're in R2, this is quickly and easily done using the law of cosines. So the law of cosines had to do with how to relate the cosine of this angle to the length of this, the length of that, and the length of that. The law of cosines is a generalization of Pythagoras' theorem. If you have vectors in R3, what you do is, if you have two vectors in R3, well, they lie in a plane. And within that plane, you can do the law of cosines. If you have two vectors in R5, those two vectors are in a plane. And within that plane, you can do the law of cosines. So all of this generalizes to vectors of any length. So if I asked you for the dot product between 6, 7, 2, 0, 1 and 0, 1, 3, 3, 2, that dot product is going to be 6 times 0 plus 7 times 1 plus 2 times 3 plus 0 times 3 times 1 plus 1 times 2. And that is 0 plus 7 plus 6 is 13 plus 0 plus 2 is 15. So we can generalize dot products and lengths to Rn. So given u and v in Rn, the length of u is simply the square root of the sum from I equals 1 to n of ui squared. And the dot product of u and v is the sum from I equals 1 to n of ui times vi. So it's just exactly the same thing as you know from before, just more so, longer, but not new. And so we can talk about the length, or the norm, of 6, 7, 2, 0, 1. That would be the square root of 36 plus 49 plus 2 plus 0 plus 1, which is some number. 4? Yes, thank you. Okay. Now, the dot product has all sorts of wonderful properties which you used all the time, but you didn't quite possibly think about using. And before I talk about the properties, let me just do an exercise from the book. Exercise. Determine all values of k such that 1, 2, 3, 4, and k minus k0 are orthogonal. Okay, so first of all, we have to figure out if we understand every word in that sentence. And we realize that the word we don't understand is orthogonal. Orthogonal is what we call perpendicular. So definition, u and v are orthogonal if u dot v equals 0. So for example, 1, 1 and 1 minus 1 are orthogonal. Those are these two vectors. That's a 90-degree angle. And u dot v is length of u, length of v cos theta. The length of this is the square root of 2. The length of this is square root of 2. And so we have that 1, 1 dot 1 minus 1 is equal to the square root of 2 times the square root of 2 times cos theta. That's by a theorem. On the other hand, by the definition of the dot product, what does that thing equal?
1 plus 1 times -1.
So 1 times 1 plus 1 times minus 1, which equals 0. Definition of dot product. So we've got that 0 is equal to root 2 times cos theta. So that forces cos theta equals 0. And so that tells us that theta is equal to pi over 2. Now, uh, 0, 0 and pi square root of 2 are orthogonal. By the definition, two vectors are orthogonal if their dot product equals 0. 0, 0, dot pi root 2 equals 0. So that means they're orthogonal by definition. On the other hand, this is equal to the length of the 0 vector times the length of the vector pi root 2 times cosine theta. And suddenly you're kind of wondering what's going on. Here we have the vector pi root 2. Here we have the 0 vector. What's the angle between them two? It's not defined. On the other hand, what's this length? 0. So we're not going to lose sleep about the fact that we can't define that angle, because if we could define it, then we'd get some number, and then we'd multiply it by 0. So what was the point of defining it? This is 0. So in high school, when you talked about vectors being perpendicular, you were always thinking about vectors that had length, and you were thinking about angles. That still goes through if you have vectors with non-zero length. But the fact of life is that the 0 vector is orthogonal. It's orthogonal to every vector. There was nothing magical about pi root 2. Anyway, back to that example. So determine all values of k so that those two vectors are orthogonal. So 1, 2, 3, 4, dot product k minus k0 is equal to k plus 2k minus 3k plus 0, which equals what? 0. So they're orthogonal for all values of k. And that's basically because this thing is a scalar multiple of 1, 1, minus 1, 0. And these two vectors are orthogonal. So it really doesn't matter what the scalar multiple is. If these two vectors are orthogonal, then any scalar multiple will be orthogonal. If you had been given the same question for the vectors 3, minus 1, and k squared, then you would have gotten that you want 3k minus k squared equals 0 is needed for orthogonality. In which case you would get that k equals what? 0, or k equals 3. So what we have figured out for that example is that 3 minus 1 and 0, 0 are orthogonal. That's the k equals 0. And we've got that 3 minus 1 and 3, 9 are 2. Okay. So properties of the dot product. Basically, the dot product is a wonderful thing. It plays well with addition. It plays well with, it doesn't care what order you do things in. It plays well with scalar multiplication. The dot product is just lovely. So theorem. let x, y, and z be vectors in Rn, and t is a real number, then, first of all, the dot product of a vector with itself is greater than or equal to 0. That is because this is, you take each component, square it, and add it. Square each component and add them together. Each piece in that sum is greater than or equal to 0. And so if you add together a bunch of things that are greater than or equal to 0, it'll be greater than or equal to 0. And x dot x equals 0 if and only if x is the 0 vector. Because this is take each component, square it, and add it up. If you get 0 when you do that, that means that every single component squared is 0. Therefore, every component is 0. X dot y is equal to y dot x. So when you do x dot y, you take the first component of x, the first component of y, and you multiply them together. From 3rd grade, does it matter what order you multiply real numbers? No. 2 times 3 is 3 times 2. So this would be a bunch of x's times a bunch of y's. This would be a bunch of y's times a bunch of x's. But because it works at the level of real numbers, it goes to the dot product. X dot y plus z is equal to x dot y plus x dot z. And finally, x dot t times y is equal to t times x dot y is equal to tx dot y. So this one, again, it all boils down to things working for real numbers. And I believe the book has a proof. But basically, the dot product is nice because at every level you're invoking something from grade 3. And the fact that real numbers distribute, commute nicely. Let's get to the big point of today's lecture, which is matrix multiplication. So up till now, I've been talking about how matrices are very similar to vectors in that you can add matrices if they have the right size, and you can multiply them by scalars. We do not, in general, given 2 vectors, you can't multiply them. The cross product is sort of like a vector multiplication, sort of, but that's only for if you're in R3. Matrices can be multiplied, and that's what we want to do for the rest of this lecture. If they are the right size, they can be multiplied. So let me, to justify matrix multiplication, let me remind you of an example. So we claim that the linear system x1 plus x2 plus x3 equals 1, x1 minus x2 minus x3 equals 2, x1 plus x2 minus x3 equals 0, has solution x equals 3 minus 1, 1/2. So the way we would check this claim is we would just plug this in for x1, plug this in for x2, plug this in for x3. So 3, 3, 3, minus 1, minus 1, minus 1, plus 1/2, minus 1/2, minus 1/2. And we want to know whether that equals 1, 2, 0. Hold on. Okay. Okay, so I've got my minuses, minus,
No, it's the first one is minus and then plus both. Because it's
hold on. So 3 minus 1. The joke is that I checked it in my office. Oh, 3 halves. 3 halves, 3 halves, 3 halves. Okay, now I'm happy. 3 halves plus 1 half is 2, minus 1 is 1. 3 halves minus 1 half is 1, plus 1 is 2. 3 halves minus 1 half is 1, minus 1 is 0. On the other hand, if we'd had the coefficient matrix, so the coefficient matrix is 1, 1, 1, 1 minus 1, 1, 1 minus 1 minus 1. And we have the solution vector, 3 halves minus 1, 1 half. We could have taken the dot product of the first row with this, and this would have given us 3 halves minus 1 plus a half. So 3 halves minus 1 plus a half is 1. The dot product of the second row with this would be 3 halves plus 1 minus a half is 2. The dot product of this with that is 3 halves minus 1 minus a half is 0. This is an example of matrix multiplication. So this is a 3 by 3 matrix times a 3 by 1 matrix, and it yielded a 3 by 1 matrix. So this is an example of matrix multiplication. Let's define it. We cannot, in general, we cannot just multiply an arbitrary pair of matrices. We require that they be the right size.